Like my vocabulary is like all like
normal words. Like normally, green.
yeah.
So you should say like normally in green.
There's a normal word.
Ah,
So like a normal word is like iridocyclitis, stuff like that.
are you there?
What about
You got X?
There she is. Okay, you can wave at everybody. I'm gonna.
Maniac
You out there? And she can see all of y'all.
It's funny because her hand is so glitchy. She's like,
Yeah, they're making fun. Okay, so y'all ready to grade it and see? I gave them this to see how many of them they can put on there.
I'm not ready to grade this because I don't know. There's one that I'm not called, two that I'm not called.
I can put this here. And here, I'll just hold it right here and you see if you can think of as many as you can, like ABC. I bet Alex is gonna beat y'all all. She's not even here.
Oh no.
She's laughing. Mine, your sun is coming in right over your head.
and
Okay, there we go.
No, those are the mints. Altoids are the mints, right?
Do you think y'all could do better if you got in pairs?
yeah.
Raise your hand if yes.
I don't care.
If you want to pair up for this, you can give it a shot.
Using you. I know, but
Not the whole group.
Yes, I'm nice.
Okay, so
So like
you can get in any group. I don't care. Where are you going? You can't reject her. Y'all are supposed to be in a group.
I thought these were oh wait, these are transition. Wait. See, it's transition.
She's watching y'all. She's ignoring you. Let me erase. There y'all go, working as a group again.
Did anybody get D? Does anybody have D?
Okay, work as a whole group. See how many y'all can get.
that's the only one I did not get.
Of course, I don't know how many people can share from one Smartie. All ready to check them?
Yeah, we're checking now.
I mean, check them like with me.
Oh, they're looking at me.
Did y'all already look at a periodic table?
No, they're looking at mine.
Oh, look at yours?
I know all
We're
of them
checking
except for one.
by each other.
Oh, okay.
Okay, so can I write these down? Somebody got a pencil because I'm too old for that. Can you spell that?
Y'all just trusting that she's right, huh?
No, we're checking.
No, don't check yet. No. I want to see what y'all get without before you check. You can check with me when y'all are ready to check. We'll check with me. Okay, let's see.
I have these in like.
This is basically, I don't know about G, but it's first to the group.
Halogen? Are those
The
pests
halogens.
just out?
Double gases, and then that's lanthanoids and that's actinoids, but I know.
Okay, then there's one name for both of them together.
Yeah, I don't know that one.
It's based on this.
Oh, I know it.
Oh, I think
I
she's
know
about
it.
to get it.
I know that one.
Let's see how far y'all got.
Uh,
Yeah, double acid, metalloids, good.
At the bottom.
What's
Oh.
NG?
noble gas.
No, that's none.
Those are not.
See, I told you.
But is it?
What's that?
Rare earth metal.
That's one name of them. There's another name that I like better.
Lanthanoids.
There's that too, but there's another one. There's lanthanoids and actinoids, but it has kind of based on this word.
Transition.
Yeah, it's kind of off of that.
Non-transitional.
No.
Untransitional.
Sub-transitional.
Remember they kind of, if you were to break the periodic table, they'd fit right up in there. Right in the inner part.
Sandwich.
They're the
Pre-trans.
they're inner
The inner core.
Intertransitional.
inner transition metal. Okay. Yeah, so let's just double check. I'm gonna say them as I go. So A, have a seat. Oh, she lost me. There we go. A is alkali metals. B is alkaline earth metals. C is transition metals. D, way over there, is chalcogens. E, halogens. F is noble gases. They've also called them inert gases, but well, that's another name, just saying. Okay, G is inner transition metals. Inner transition metals. Post transition.
I thought that was one.
It's inner transition. They are also called the rare earth metals and actinoids and lanthanoids. Yeah, we lost that one. Okay, and then H is metalloids, and I is metals, and J is non-metals.
Okay, so I got two wrong. Because I
Oh,
didn't know C, but I technically got that right because Brianna told me.
Mm.
Left, what's the last one?
Metal. It's metal.
left side of the shaded area is the metal. All these are metals.
Then what was the J?
Is the non-metals. Get it? Metals, non-metals.
So, do we all get learning?
I don't know. Nobody got them all right. Y'all could all share one, but COVID probably wouldn't like that. Yeah, I guess y'all did pretty good.
Oh, that's so nice.
I'm gonna have to get some more before I come back from break.
Unmute yourself.
I'll send her a virtual Smartie, maybe. Maybe when she gets back. Woo.
Thank you.
Catch. What?
Oh,
Those reflexes, I don't know.
I caught it.
It landed in your lap. Okay, now let me get my book. And y'all get your books out. Yeah. How do you remember them from? From this course or from an earlier? From this course. Wow. Things just stick in your brain pretty good.
forget stuff that I read often. Do you have a photographic memory? I don't have a photographic memory because I forget stuff.
Oh, the Raj had photographed.
I can imagine that.
Yeah, he's done me.
I can like memorize the math. But like words.
Old Mr. Smith was that way.
I can do words pretty easily. I have to read it once or twice and then make it right. What are we doing?
Okay, so we are going to finish taking notes on this chapter. Couple little things. We talked about electronegativity was where we were. Were y'all writing stuff down? You might want to get that stuff out again. And one of the reasons I keep asking you these things is because we are going to have a quiz over some of this. I was going to have it tomorrow, but I meant to tell you yesterday, but we didn't have class yesterday. I was going to tell you Tuesday, and I forgot. And so we're going to have it on Monday.
We don't have it. Oh, wait, yes.
No, we don't.
Oh, we don't.
You're right. Oh, darn. We could do it tomorrow. Could it be? No, I couldn't be an open, but part of it is doing just what you were doing. Another part was who invented the periodic table?
Mendeleev.
Then
Mendeleev.
Bro, that's who we're reading.
Mendeleev. Okay, and why was he given the credit? There were special reasons.
Because he organized it and was able to
Organized
predict
in a
it.
certain way, and then he predicted more of them.
He left gaps for the ones that were missing and predicted what their properties would be. Yeah. So that's one of the questions. And you have to label some stuff. And then what was the other question? There was one about the actual trends, like for atomic radii, what is the trend as you go across the periodic table?
They
Decrease.
get bigger.
It increases, decreases.
No, the size gets smaller as you go across. And what happens as you go down? They get bigger. What about the ionic size? What does it generally tend to do as you go across?
Increases.
No,
It still decreases, but remember it'll all of a sudden explode up here when it gets close to the non-metals. It'll get big, but then it'll get small again. So it's still a decreasing thing. But and as you go down though, the ion sizes increase.
I like that thing.
That thing.
The
what?
thing, that thing.
Oh, this. Yeah.
That thing.
She's, yeah, it's pretty weird. Then there was ionization energy. And what is ionization energy? The energy required to what? Yeah.
When you gain or lose an electron.
Well, that's not what ionization is, but the ionization energy is only the energy that happens when what happens? With one of those happens. Which one?
When you lose an electron.
Yeah, taking an electron takes energy. So the ionization energy is the energy that's required to remove an electron. And so it has trends too. How does the ionization energy, what happens to ionization energy as you go across? It's opposite the other ones. It gets bigger. It becomes easy. You get more, it takes more and more energy to take an electron, right? Because since the sizes are smaller, the electrons are closer to the nucleus. So it takes more and more energy as you go across. But it takes less and less energy as you go down. It decreases this way because those electrons are farther out because it's taking valence electrons and they're further away. So it's easier. And then we talked about electron affinity back on page 113. It's got the same trend as ionization energy, but it's the amount of energy released when adding an electron. So if you add an electron, you get more and more energy as you go across. See, atoms over here, elements over here want to lose electrons. And so adding electrons takes a lot of energy to add them. But as you go over here, these guys want to lose electrons. I'm sorry, want to gain electrons. They want to gain them, so the electron affinity becomes less. Hang on, was I doing that right? I know that it increases. And so the amount of energy released increases. I have to remember that the energy is released. And since they want to gain those electrons, the energy, they release a lot of energy because it makes them much more stable. Okay, the main idea is for the ionization energy and the electron affinity, it increases as you go across, and then it decreases as you go down. Okay, and then the last thing was electronegativity. Remember that? Electronegativity was a measure of how strongly atoms attract the electron shared between atoms inside molecules. So think about this. Let's say you and, I don't know, pick someone in the room, like partners again.
Yeah.
Okay, there'll be someone left over, right? Okay, somebody can pick with Alex up here, okay? So pretend like you and that person has to share a cell phone. Okay, so you think one of you is going to want the cell phone more than the other one and have it more often for longer periods of time? Or do you think you'll share it pretty evenly?
I think she would get it more often because I always get grounded. So
So probably that.
I want it more too, honestly. But
Uh-oh.
I'd be grounded. I'd be grounded.
You'd be
so I think
grounded.
she'd get it.
I would love to not even have to mess with my phone. A lot of adults are like that, but I do end up having to use it a lot for school and everything else. But I would love to be able to just let someone else take it. But that's kind of like a measure of, how much you want to grab or hold on to something that you're sharing with something else. So an atom is sharing, a lot of times we'll be sharing electrons with another atom. That's called a covalent bond. and the measurement of how strong they attract those electrons is the electronegativity. Okay, and so if you would have a high electronegativity if you want to hold on to that cell phone more than your person you're sharing with. Let's say you think about that same person and you want to share chocolate chip ice cream. Would you want half of the container or most of the container, or let them have most of it? Half and half? Okay, how about cookies and cream?
Yeah, you can have it all. If I get chocolate chips, then you can have the cookies and cream.
My favorite is either the intense chocolate.
I like cookie.
I like chocolate mint. I like the cookie dough.
I like salted caramel. I gotta say salted caramel.
Yeah, I like strawberries in there too.
I hate strawberries ice cream. I hate it. Like I cannot
Weird.
eat artificial chocolate.
That's not even real chocolate. Okay, so electronegativity is the measure of how strongly an atom is going to attract electrons. And the interesting thing, if this follows me, these elements over here in the corner, not the noble gases, they don't care about anything. They just want to be left alone, all right? But these guys over here have the strongest electronegativity. Fluorine is the electron hog, okay? It has the highest electronegativity. So knowing that fluorine has the highest electronegativity, what do you say? What's the trend as you go across? It's going to increase all the way to fluorine. What happens as you go down? It's going to decrease. In fact, over here, I guess it's radium, rubidium. I think, no? Francium. Yeah, it's francium. Francium in this corner has the lowest electronegativity, like really close to 0. And it's a scale of 1 to 4. And old scales used to have fluorine right at 4. Nowadays, it's at 3.98. I don't know why they changed it. And there's no units to it. It's just kind of on a scale of 0 to 4, how strong do you attract electrons, you know? And these other guys, and they're kind of red right here, nitrogen, oxygen, fluorine, chlorine, those are really the biggest electron hogs, but especially fluorine. Okay, and you're gonna have to know that, like, what is the trend and what element has the highest electronegativity? Fluorine, 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 fluorine. And which one has the lowest? Francium. They both start with F, but fluorine and francium, you have to know that. Okay, and it asks how the electronegativity scale was developed on one of the quizzes. I don't know if it's the next one or the one after that, but it talks about there on page 115 about Linus Pauling. And he was, I know Linus is a kind of a weird name, but I know people know that name. Probably when we get back. I'll just have to review everything again. We'll review it first. First thing you come in, hand it out. No. So Linus Pauling was studying chemical bonding. That second paragraph there on page 115 says, in 1932, as part of his efforts to understand chemical bonding, he introduced what is now called the Pauling electronegativity scale. Okay, and so he's the one that came up with it in his efforts to understand chemical bonding. And I think it's interesting because when I was in college, I majored in chemistry, and I actually used these books, I think for sure, Chemical Bonding and the Structure of Molecules. And by Pauling, but they mention him. It's all based, all of this is based on Linus Pauling's stuff. And that was, you know, about 50 years after he had come up with all that. Okay, so electronegativity. Now they look at the bottom of page 115. What kind of molecule is that? Open your book. Open your book. Open your book. Water, that's right. Did you recognize it or did you have to read it?
I read it.
Okay, you need it. I used to have them hanging up here. I took everything down when I thought we were going to move. But it's a water molecule because it's H2O. So the H is the red and the 2 oxygens are the white ones. And It talks about how electronegativity affects a water molecule. I'm going to draw it up here. So say this is the H2. So I'm going to have to do this. Okay, here's the O. And they always have it in this kind of a shape rather than sticking straight out, or if you flip it over, it's more of a kind of a Mickey Mouse thing. And there's a reason that it's shaped like this, and we're going to get into that, I think, in chapter 5. But the deal is that oxygen, remember oxygen's way over there by fluorine? And so this bond right here is not really a stick, it's actually 2 electrons that are being shared. That's what keeps them together, because you can't share something with someone else if you aren't close to them, right? And so, but the deal is that oxygen wants to attracts them a lot more than hydrogen does. And so it pulls the electrons. They spend more of their time around oxygen than around hydrogen. And one of these electrons is the one electron that hydrogen has. Now over here is just kind of like its nucleus by itself, which is just 1 proton. So this is just like a naked proton out here, which is all this positive charge. And here's another one, all this positive charge. And this oxygen has, since it's hogging these electrons, it's mostly negative, right? Because electrons are negative. And so when you look at the molecule overall, it's got a negative side and a positive side. Every little molecule of water is what we call polar. Yeah, but it's not, well, I guess it is electrically polar, yeah. And so if you have something that is negatively charged, have you ever seen people with, they run a thin line of water out of the hose and then, or the faucet, and then they can make that, the water kind of bend, the stream of water will bend?
I haven't seen that. Can you do that?
I'll have to practice in here. I don't know if I can get a stream of water smooth enough, and I forget what they use. I'll have to look it up again. And I've seen it on videos. And it's because of this polar idea of water. Have y'all learned about water being polar in the past?
I think you mentioned it.
Okay, because no, I think they talked about it in 9th grade at some point. But anyway, it plays a major role in the weird properties of water. Y'all are so used to water just being everywhere, and life is based on water, and you think water is the normal thing. But water is totally, it almost breaks every rule. It's really different than you would expect it to be, because think about it, it's a little molecule, just 3 atoms. There are a lot of molecules that have hundreds of atoms. It only has 3 atoms, and most atoms, or most molecules with only 3 atoms, especially small atoms like those up there, are gases at room temperature. Think of carbon dioxide, CO2, it's a gas. Methane, CH4, it's a gas. Most things with the molar mass of water, it's a gas at room temperature, but water is not. And it's because of this polar bond, this polarity. It's a polar molecule. It exhibits polarity. Okay. And what happens is when you get a bunch of water together, the negatives and the positives, they attract each other. Right. Just like if you had a bunch of magnets, when they all attract each other. And molecules in gases are spread all out, right? But when they attract each other and get close together, it makes it a liquid. And so, and then there's a bunch of other things we'll talk even more about in another chapter. Well, I think we have already talked a little bit about the things that, like ice expands when it freezes, water expands when it freezes. We didn't talk about, it was in the introduction, I think, but it's because when it starts to freeze, that means all the molecules are going to get into a certain position, and they're going to stay in that position as a solid, right? Molecules in a solid kind of stay in their position. And if you have a little plus minus side, well, then you're going to get a plus here and a minus there and a minus there and a plus there. And but it ends up ordering itself in a hexagon. You've seen hexagon? Yeah, the water molecules line up in hexagons, and so they have to spread out to get in that hexagonal form.
Is that the lattice crystal?
The crystalline structure, yeah. And that's why snowflakes end up having such beautiful patterns, and they're all hexagonal, even though they're very different from each other. Like if y'all were all kind of just all talking and kind of grouped up in a group, like a little huddle or something, and then I said, okay, everybody hold hands in a circle. Y'all would spread out, right? And that's what water molecules do. And most things, they get denser when they freeze. And so if I put ice in a glass of water, the ice stays at the top. But if I put a chunk of wax in some melted wax, it'll sink to the bottom. And that happens with just about everything. It sinks to the bottom because it's usually denser. But water's not like that, which makes a difference in a lot of things. Like if ice were to sink when it freezes, then ponds and lakes would just freeze all the way through. But now they freeze on the top, they float up there, and then they insulate the water underneath from getting that cold. And so the fish can survive, and the turtles and all the other things. And so there's a lot of interesting things about water that, because of this polarity, it has we get what's called hydrogen bonding. Have you all heard of that? Hydrogen bonding? Yeah, we're going to talk more about that. And we did already, but I think we'll talk more. And so hydrogen bonding is important. So anyway, he talks about that a little bit on 115. And diagram 414. Yeah, look on page 116. He shows where francium is and where fluorine is on the bottom of the page. And see how the arrows are pointing toward fluorine, because that's the highest electronegativity. And then francium down there is the lowest. Okay, now we're going to talk a little bit about hydrogen. See that last little section, 4.5 on page 116? There's just a few paragraphs, and then we're ready to go into the exercises on the next page, right? So let's talk about hydrogen. Hydrogen is weird. I mean, we already know it's weird because it's in water. And when the universe, like after the Big Bang, at the very first few tiny parts of a second, milliseconds, nanoseconds or whatever, you didn't even have protons and electrons and neutrons yet. But once they started forming, everything, a lot of them turned into hydrogen. That was one of the first elements that got produced in the Big Bang. And a few things combined to make helium, but for the most part, everything was just hydrogen and helium in the whole universe. And eventually gravity caused some of it to condense on itself and become suns and stars, you know. And then you started getting, because of the pressure, you started getting the higher elements getting formed through fusion, okay? But for the most part, even now, I would say 99% of the matter in the universe is hydrogen and helium still. I mean, even with all this, like our sun is mostly hydrogen and helium. And it's huge compared to the little planets that it has around it, right? And so most of the universe is hydrogen and helium. And so astronomers, they talk about hydrogen and helium, and they call everything else metals, even the non-metals, they say anything other than hydrogen and helium, those are just heavy metals. Question?
Why is the sun so hot?
Well, there's so much hydrogen that the gravitational attraction pulls it in toward itself, and it just it produces a lot of pressure, and they start hitting each other harder, and you have all this pressure, and then when they're hitting each other, they tend to spread out. So there's kind of the hydrogen's pulling it, I mean the gravity's pulling it in, and the energy is trying to push it out, but there's enough gas that it gets compressed enough to start thermonuclear fusion, and that produces a lot of heat. And so that's where the heat comes from for the most part. There's for some reason the very outer edges of the sun are like, they have the sun right here, and they have what's called the corona, you know, that's just around the outside. It's all gas, but you get real thin gas, I guess, out here. And for some reason out there, it's even hotter than it is down in the center of the sun. They're not sure why exactly yet. Still trying to figure that out. And they've sent out a satellite that actually, you know how we go around the sun, the Earth goes around the sun? So does this satellite, which is pretty amazing because all the other satellites only go around the Earth. But to make a satellite that goes around the sun, it's pretty incredible. And it has a real, like here's the sun, it's got this real elliptical orbit. And I think it goes around Venus too. I don't remember exactly, but it's pretty fascinating what they're doing. And they're finding out a lot about the sun and about hydrogen and helium. But you notice how, especially look at the periodic table on page 117. What color is hydrogen? Orange, right? Around all the other orange ones? No, it's way over on this side, and all the other orange ones are way over on that side. What's the deal with that? And it seems like helium, they either should move helium over here, right? Or maybe they should move hydrogen over here. Makes sense. But then you think, well, helium really should stay with the other noble gases because it's non-reactive. But hydrogen is actually kind of schizophrenic, kind of multiple personality kind of thing, you know? And that's what we're going to talk about here. And so it says that hydrogen is located in group 1. Let's get a marker that works. Hydrogen is located. What time do we get out? 10? What? Okay. Yeah, we can do this in group 1 because of 3 reasons. There's a couple of reasons, but it's actually 3. Its electron is in an s orbital. And remember, all this is the s block over here. Everything over here that's outer energy level is an s orbital. And so hydrogen has an s orbital, so it's in that same group. 2, it usually loses electrons, its own electron. It usually loses its electron. And remember what metals do? I'm a metal, I lose electrons, right? And so this is the metal side. So it should be over on this side because it loses electrons. And then finally, it says that 3rd, in an aqueous solution, acids, which are formed with hydrogen, will dissociate just like ionic compounds do. And so you don't really know what that means yet, but it disassociates. How do I spell that? There you go, associates. In water. Even water itself, H2O, it disassociates in itself. Okay, and for instance, let me give you, just to give you a little idea what that means. You can have HCl and you can have NaCl, okay? And you can even have KCl and these other things, lithium chloride. You put these in water and they'll dissolve. They'll break apart. And that's what disassociates means. It'll break into Na, sodium atoms, and chlorine atoms. And HCl does the same thing. It'll break up into hydrogen and chlorine. So that's what we mean by the disassociating, like the other alkali metals. Okay, so that's 3 reasons why it seems that it should go there and act like all these alkali metals. All right. Let's see, hydrogen's atomic structure and its normal ionization as a cation with a charge of +1 indicates it belongs in group 1. Let's see. That's kind of what it says here. It usually loses an electron or it has a charge of +1. Its usual charge is +1, just like the other alkali metals. However, I'm gonna go to this side of the periodic table. And bring Alex over here too, so she can see what I write. There we go. Hydrogen structure. Alex, come on. Okay, how about that? Can you see? Can y'all still see? No. Right here. Okay. Hydrogen structure, it's on the bottom of page 116. Oh, I'm sorry. Its structure determines all this. Okay. I should have said that. Its structure. Okay, so on this side over here, its behavior is more like a halogen. Where's the halogen? Yeah, if we slid it over, it'd be right above fluorine, right? Then an alkali metal is more like a halogen than an alkali metal. And how so, you might ask, right? Well, 3 ways again. For one thing, hydrogen shares electrons in covalent bonds. We'll talk more about what those are. Hydrogen shares electrons like nonmetals do. And so when you have like CH4 and all the carbohydrates, it's sharing electrons. Carbohydrates. I mean, carbohydrates obviously have hydrogen in them, sharing electrons. Metals, they don't share electrons. What they'll do is they'll lose their electrons, just completely lose them. And then they will be attracted to other, they become positive cations, and they'll just be attracted to negative ions, and they'll just build up a big crystalline lattice. Okay, so it shares electrons. You can also say it forms molecules. Metals don't form molecules. Metals form those crystalline lattices. We'll talk more about that later too. And number 2, hydrogen bonds to itself. Like when left alone, if you have a bunch of hydrogen atoms, they're going to pair up to make H2, hydrogen gas. It's always 2 hydrogens bonded together. And that same thing happens to all these halogens. You get F2, Cl2, Br2, I2. Okay, all these bond with themselves, but none of these guys will do that. They don't do that. Okay, and finally, hydrogen can, it doesn't very often, but it can ionize by gaining an electron. Gaining, yeah. It normally loses its electron, but it can ionize by gaining an electron. And when that happens, you get what's called H with a minus there. It's called a hydride ion. Hydride ion. Whereas over here, when it loses its electron, it becomes a hydrogen with a +1 charge. Look at that, H+. We normally see it as H+, but it can do this, just like all the halogens. So hydrogen is unique among the elements in the periodic table. And so you're going to have to know these, why it's like an alkali metal, but why it's also like a halogen. And you could highlight it in your book if you want to. I basically just kind of took it out of these 2 pages, 116 and 117. Okay. Any questions, comments? Pretty amazing stuff, I think. So we're going to be working on the exercises now pretty much for a while until we get all the way through 29. That covers all the chapter 4 exercises. And then from 30 to 43 is review exercises from reviewing chapter 1s, 2, and 3. 30 to 43, yeah. And so we'll be doing that eventually. And then finally, we'll take the chapter 4 test. And then about then we'll probably start reviewing so that we can take the semester exam. Because I mean, that's going to happen real quick, right? Because we've got tomorrow, we've got Monday, and then we're gone for the rest of the week, and we're gone for the following week, and then we're already into December. All right. And then we only have a couple weeks before we get into the reviewing for the finals, then we have finals. So it's all going to just snowball and we'll just go fast. What is final? No, your final is only 20%. It's 20% of your semester grade. 20% of your semester grade. So what they do is they say 40% for quarter one, 40% for quarter two, but we don't even do quarters in chemistry. It's all just 80% semester one and 20% the final. Okay. And it is, it says 11:07. That's appointment. I've been getting a lot of notifications all during the whole time I'm lecturing. Never fails. All righty. Well, any questions from Alex? You doing all right? No, you feel okay. All right. Well, then I'll hang up. Talk to you later. Everybody says bye. She says bye to everybody.